That's good. Let me just put that there. Any confidence interval you create could be the one that's wrong. That's why it's just like science. Statistics really is like science. It's all about repeatability. If you have one study that says something, you don't publish a damn thing until somebody else somewhere sees that same effect. Then you're really pretty confident. Then you're like, you're even more confident that two separate ones said the same thing. You feel pretty good about that. Does that make sense? So people often misinterpret confidence intervals because they only have one study that says something. So you always have somebody say, well, you think, eating 500 eggs in one morning is bad for you. But this one study from 27 years ago said it was fine. Okay, dude, whatever. I'd say it's bad. But do you guys understand? I mean, that's a silly example, but we see that all the time. This one study said this. That's one study. That's probably the study that was wrong. There's always a chance that something's wrong. So there's always going to be something that's wrong somewhere. But if you have several that all say the same thing, I'm like, that's really strong evidence that this thing they're saying is right. Okay, maybe. This is where people lose faith, as if you need it, but lose faith in statistics. And the stats is just like, dude, this is what I see. And I could be wrong. And that's beautiful. I love that about it. The fact that it could be wrong makes it stronger. It's being honest. Okay, I'll stop. So does that make sense by itself, this problem? It feels just like an X bar problem, just like a mean problem, the same kind of work. The formula is just a little bit different because it's got N's and P's and Q's in it, so it's got to be different. Okay, so let's try something with T-scores. Let's try to use this chart, and let me explain degrees of freedom, what the hell that means, because I didn't get into that last time. Where else did we see n minus 1? That's what degrees of freedom are. I think I said that last time, right? Degrees of freedom is n minus 1? If I didn't, I just did. So degrees of freedom is basically just n minus 1. So if you have a sample of 17, your degrees of freedom is 16. That's crazy, right? You're like, ooh, that's amazing. Somewhere way earlier this semester, we saw n minus 1 instead of n somewhere.
It's the sample standard.
Sample standard deviation. I love it. So that also had to do with samples. This has to do with samples. There's something about samples that requires this degrees of freedom. So what the hell, why do I call it degrees of freedom? It's not just me. But why do we call these degrees of freedom? So let me come at you with this. All right, so right now, just make sure everybody's on track. I'm explaining what degrees of freedom means. This is not a part of a problem you have to do. I'm just explaining what it means. Right? Say I had 4 numbers. I would have loved if everybody was, I have 4 numbers. But say I have 4 numbers, and I know the average. I want the average of these numbers to be, it doesn't matter, 10. I want them to average to be 10. Let me see if anybody can answer this. Do you know what any of the numbers are? If they average to be 10, do we know what any of them are? Do any of them have to be 10?
Yeah.
No. Could one of them be 18 billion? Of course, as long as another one's like negative 18 billion, right? So but I do know something. I know one thing very specifically about what all 4 of these numbers have to do. I don't say they have to average to be 10, yes. But by saying this, I know something else. They have to add to be 40, of course. How do you get the average? You add them up and divide by, in this case, 4. So what do you divide by 4 to get 10? 40. So I know the sum has to be 40. That's the only restriction on this. How many numbers can I just pull out of nowhere until I have to be careful? Do you understand the question? So do I have to make this first number anything specific?
No.
It could be anything. Give me a number. I love the 10%.
Pi.
Just make them all 10, Jeff. Oh, okay, pi. All right, no, let's not make it. If I make this pi, I just need like a negative pi somewhere else. Do you understand what I'm saying? Just to cancel that shit out. So let's make it 7. Sure. Nothing too crazy, but not 10. Does the second number have to be anything? No. Give me another one that's not too crazy. 12. Okay. And the third number, does it have to be something specific?
Right.
It could be anything. 3, I love it. Now that last number, oh shit. So how much freedom, if I had a sample of size 4, how much freedom did we have? 3. That's So degrees of freedom tells you how many data points you could just assign arbitrary values to, and the last one, there's one left that has to make the whole thing work. So that's the idea of it. I can't get into the real math of why that kind of sneaks in, but it has to do with the fact that we're talking about samples. So it's a little bit hazy, but that's where at least this idea comes from. That's why we call it what we do. Right? So what would this last thing have to be? 18. How'd you guys get that? I like it. The way I would do it is, this is 3 below, this is 2 above, this is 7 below. So overall, I am 8 below, so I need this to be 8 above 18. Sweet. Uh-huh. How below 10 is this? 3. How far from 10 is this? 2 up. How far from 10 is this? 7 down. So my last one has to be 8 up from 10 to make the whole thing come out to be an average of 10. That's a quick way to do that kind of problem. Yay! Some of you guys are like, whatever. No, you don't have to do that. It's just another way to do it. That's all. That's all. Okay. All right. Anyway, all right, so that explains why we call it this, and that explains why it is this. Those two go together. I love it. Okay, so let's practice just using the chart itself. So say I need a T-score for a 99% confidence interval where n is 11. Do not say anything out loud. Try to find the T-score that you need. All right, let me catch up to you guys. Which column are we looking at? First, second, third, fourth, fifth? First, because I know there's 1% in 2 tails. So that first column I'm looking at. I'm going to start to go down, but I'm going to stop where? What's my degrees of freedom? 11 minus 1? 10. I like it. I guess you guys should see this. There's nowhere safe to put you on. So I know I want to use this column because it's 1% in 2 tails for a 99% confidence interval. I go down until I get hit to the degrees of freedom, which is there, not there, there. So my T-score would be 3.169. If it was a Z-score, if I was allowed to use a Z-score, it would be 2.576. The T-score just forces me to be more conservative. There's a part of my problem I'm not sure about, the standard deviation, so it just makes my confidence interval a little bigger. I catch more stuff to keep the same confidence. What's rocking my confidence? I got S. I don't have sigma. And my sample is so freaking small, that's why the score's got to be a decent amount bigger than it normally would be. Okay, maybe. All right, so what about, what if I want a T-score for 80% confidence, and my sample size is, what you got, Jeff? I don't know, Jeff. Well, we'll do 83, like you said earlier. All right, so which column am I looking at? Last one. What's my degrees of freedom? 82. 82. Is there an 82 on this chart? No. So you're always, or almost always, and let me show you an example of where you're not. You're always trying to be more conservative. pretty much always. But so if I get 83, I'm not going to go up to 90. I'm going to go up 82. I'm going to go down to 80. And why do you think this chart does that? Here's changing by ones, and then it starts changing by fives, and then it's tens, and then it's hundreds. Because the T-scores are not changing as much anymore, so they can kind of skip a few, right? You guys kind of with me. So I would use what then? So I'm looking at the last column.
2.639. Oh.
1.292. You guys with? Just
Not 85 or 86. Can you go to 90?
Yeah, that's where it starts to get, the closer you get to 90, the more okay it is to jump up to that one. I would say down here, you just always go down. But when you get to like 293 degrees of freedom, I'm going to use the 300 number. I'm not going to go all the way back down to 200, right? So pretty much I try to not give you that kind of problem, or if I do, I'll let you have some leeway, because obviously the calculator can do every T-score that exists, right? I don't know what's going on out there. But we're using this chart because your crazy-ass teacher thinks that this helps you in some ways, believe it or not. So it's not going to be as precise. Or you're kind of letting go with that. I guess kind of a little bit. So if I had a sample size of 48, degrees of freedom 47, I would use 45. I would look there for my T-score. Okay, cool. Maybe. Okay. So, you guys feel okay about how to use a chart, hopefully. All right, you can tackle any problem now. Let's try one out. And I'm going to remind you about one of our stats. So the kind of problem you're going to see, possibly, we'll do two problems here real quick. I'll give you one that gives you everything you need, and then I'll do another one that just gives you data, and you've got to calculate what you need. So one kind of problem would be take a sample of 46 broccoli spears. I don't know where that came from, and find a mean of 1 point, let's say 2.7 inches of this broccoli spear with a standard deviation of 0.98 inches. You're trying to sleep, and all of a sudden your brain said, how varied are broccoli spears? So you had to go down to your nearest grocery store and do this. If you have insomnia, this could possibly happen. Same example, blah, 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 blah. Okay, now watch this. You ready? Can somebody tell me why T-scores were invented? Yes, sir.
Because it dictates the error, right? The less you have.
No. Not quite. Why were they made? Why were they invented? We already had a confidence interval formula that told me the error bounds. Why were T-scores invented? For when I don't know what? The population standard deviation. So T-scores were invented. In fact, the whole story is this dude that worked at the Guinness brewery. It's a fun word to say because it makes you sound like you've been drinking some Guinness. Make sure I say the word brewer. And he was trying to publish some data, and he wasn't allowed to as an employee, so he made up a name. He called himself Student, and he came up with a T distribution to discuss the variability in the Guinness. And he was trying to publish some paper somewhere, and that's where the T distribution came from. It's called the Student's T distribution because that's the name he made up for himself. So T-scores came from Guinness, basically, right? So I really, and if you look at the formula, just look at the formula. Again, the formulas are beautiful notes that you're not allowed to have, but I have to let you have formulas. You use T-scores when you only know S. You use Z-scores when you know sigma, right? So T-scores were invented to cover our ass from when we don't know sigma. We don't know the real standard deviation of the whole population. We only have an estimate, S. That's why they were invented. So when must I use T-scores? when I only have
Sample.
S, when I only have the sample standard deviation, right? So which standard deviation do I have?
Sample. No.
Where did these come from? The sample, there you go. Did it say sample standard deviation? No, but it said we take a sample and we find this. So where did these come from? Both of them? The sample. So you know this is S.
Yeah.
I'm telling you this because me and the book, we're not going to tell you. Right? If it's a population standard deviation, I'm going to make sure you know, because that's a day, man. If you're a statistician, I know the population standard. Holy shit! So you're going to tell everybody, hey, Larry, what? I know this. Oh. So it's going to be very obvious in the problem. They're going to have to tell you population standard deviation because it's weird. I normally don't have that. Here, it's kind of like, well, which one is it? Well, if you're not sure, it's got to be sample because it's the one you normally have. So how can I summarize what I know so far? 2.7, what would I use to denote that? X bar, I love it because it's a sample mean. 0.98. S. Cool, I like it. So that's what I know so far. So now I want to find I didn't say that, all right, good. Find the 90% confidence interval for the true mean length of broccoli spears. This is a heated debate. My whole country's go to war over this. Thankfully. Well, some things go over war as stupid as broccoli spear length, but oh well. So what did we figure out? I have to use what kind of score? Which formula am I going to use? Do we know S or sigma? So I probably want to use a formula that's got S in it, right? So that tells me I've got to use a T-score. I'm really trying to help you see in the problem how it's telling you what formula to use. So how do I figure out the T-score? With my degrees of freedom, good, is 46 minus 1 is 45. I want a 90% confidence interval, so what's alpha? Remember, alpha just means the area in the tails. 0.10. 10% in the tails, right? There's 90% inside, there must be 10% outside, right? I like it. God, I can't read you guys at all. I try to gauge where you are, and you're all like, I give you nothing. Fine. So what's this T-score that I'm going to use then? Let's see. 45. Who is it?
1.679.
I like it. So I want 0.10 and 2 tails, 45, 1.679. Make sure that you can find that and that you agree with that. We could all be wrong. But we're not. All right, cool. So and now here's my formula. I've got everything I need. I know X. They had to give me X bar. They did give me X bar. They gave me S. I know N. And the T-score I looked up. Right? I've already forgotten it. You have to remember. 1.679?
Yeah.
Okay. So I got, where'd it go? 2.7, give or take. 1.679 of these. 0.98 divided by square root of 46. I like it. Let's see if you can plug that in the old calculator. No, Jeff. So I got that for my error. So what you guys got?
Yes.
So 2.7, give or take 0.243, 0.24. I like it. So then you just gotta add it to it, subtract it from it. So your little interval. What's your little interval? 2.9. That's not good enough, of course, for Jeff, that dork. He wants you to do, that's nice, that's a good calculation. Now you got to write your little statement, your little conclusion. What's that going to say? We are 90% confident that the interval 2.46 inches. I love it. We're talking about physical reality. Bring in some units. 2.46 inches to 2.94 inches. Contains the true mean length of broccoli spears. Great singing star of the vegetable world. It's really bad pun. I don't care. I thought it was funny. I like it. So several things could throw this off. I mean, we're assuming that the sample I took was truly random. Anytime you have a sample that's not truly random, it throws off any damn thing you're trying to do. So, does that make sense? So anything I'm trying to do, if my sample sucks, my data can't be trusted, right? So we're assuming we got a decently random sample, right? That's one thing. And of course, calculation-wise, hopefully that comes out right. All right, so let's try one where we have to calculate our own mean and standard deviation. And then I've got a little handout I want you guys to work on. That's right, this is the clockless room. Okay, so in the homework on a quiz or a test, I'm going to give you a problem like this. Light bulb longevity is normally distributed. We take a sample of, say, 21 light bulbs. No, good Lord, Jeff. Let's say 9 light bulbs. And record their life, record their longevity, not their life. This is your life, light bulb. Record their longevity, their length until they stop working, right? And this is what we get, measured in, let's say days. This is some kind of weird ass old light bulbs. So let's say I get 592. 607, 581, 511, 611. I like the number 11. Okay, 672, 504. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9. I just showed off. Down to 9. So they're going to give you the data itself. You have to calculate the X bar and the S. I will never make you do the X minus X bar squared table, again, like I promised you. You just have to do 1 var stats now, right? Get this, so this is a good review of how the hell to do that. So try to get this into your list and calculate X bar and S. If you're not sure how to do that, work with somebody near you or call me over. X bar.
No, what's the confidence level?
Oh, I just want you to do that first. I want to make sure everybody's able to do that. Well, in case you get done with that soon, find the 99% confidence for the true mean length of life for these poor little light bulbs. to jog your memory. In case you forgot, hit stat, edit, and then you can start putting stuff into these lists. Just need the first list. There you go. So somebody remind me, once you get them into the list, where do you go from there?
Stat. Calculator.
Calc.
One bar.
One for stats. If you have the newer one, it's going to ask you some stuff. If you have the older one, you just have to enter. It defaults to list 1. Oh, neat, man. Sorry. I always like it when the mean comes out. A nice round number when I just made shit up. It's very unlikely. So what's my standard deviation? Yeah. What is it? I'm sorry, do it again?
61.8.
Yeah, so 61.802. And this one would be if what?
It was
If it was a population. So why does it give me both? Because it's just poorly calculated. It doesn't know what I'm doing. Right? So here you go, human, whatever. So we have to pick the one that we know works. We have a sample, so we better use the one that's a sample. I like it. Cool. So we have S. See how it has SX, and that just means it's for individuals, right? So 61.802. And now it's just like the problem we just did. That gave me the X bar and the S. So this just adds one step. They just give you data, you got to get those. Once you got them, you're golden. What's my Z-score? Am I going to use a Z-score or T-score?
T-score.
T-score, I like it, because I only know S. Is my sample big enough to be normal?
Bigger than 5. Technically.
How big is it supposed to be? Bigger than 30. But why is it okay that it's not?
Could you said
Very first thing I said, yeah, good. Right? So there is at least one problem in the homework that doesn't say that. Do it anyway. But you can say, well, this really isn't normal, but here you go. All right, that's fine. Same thing on the test. I'm basically never going to give you a problem where if you didn't notice it wasn't normal, you wouldn't have had to do all that work. Ha ha ha, I'm not going to do that to you. You would have gotten done with the test if you would have realized this trick. Ha ha. No, screw that shit. So if you think that it's not normal, just say, I don't see where this is normal, but I'm going to do it anyway to cover my own ass. I'm going to do it. Yeah. Don't just skip it. All right, so how do I figure out the T-score then? Yeah, so my 99%, so the first column. I like it. My degrees of freedom is 8. Cool. So I get 3,355.
Yeah.
Okay. And now I just got to plug stuff in. So my T-score is 3.355. X bar 565, give or take this many. Got it. Standard deviations. The next kind of biggest mistake I see is somebody puts an 8 here. Why would they put an 8 there? That's the degrees of freedom, but the formula needs an n there, right? Not n minus 1. So be careful about that. 3.355. Is that what you guys got for the error?
Yes.
I like it. And again, we would normally say 69 is a big ass error, but my data itself is a little bigger than what we've been looking at before, so it makes sense. So it'd be 565, give or take 69.1. So we are